Okay, so here we are. We're going to talk about in-place animation. I'm going to go through this relatively briefly, mostly because I want to get, I think the locomotion section will be of more use to more people. And so I'm going to put uh, a little bit more detail into that presentation, but I wanted to let you guys know that in-place animation was here and just kind of what it's about. All right, so up here we have the shelf tools. These little presents over here are actually examples, so you can drop those down and study those to kind of give you something to work off of. The shelf tools on the left over here are basically some tools that we're going to be using to construct our simulation. Generally, the way you want to work is from left to right. When setting up a sim, you don't necessarily have to do all of the steps, but executing some of them in whatever the appropriate order is meaningful. So here, agent, agent clip, those are things that you probably do all the time. Populate, something you might do, but you might skip collision layer and collision configure joints if you're not using Ragdoll. And then simulation. Okay, so let's start by dropping down a rig. So mocap biped 3. This is just a rig that shoots with Houdini. No big deal. And we're going to change the animation type to walks and turns. We'll change the walk cycle to male R001. And there we go. So the reason why it's called in-place animation is because you have an agent or a character who's walking in place, as opposed to this, which is what we refer to as locomotion. So let's rename this node to walk. I'm going to copy and paste this. Actually, Alt, drag, give me a copy of it. Rename this to run. And change the animation type to run, and there we go. Keep it at in-place animation. Let's check what we have. Perfect. Okay. Then let's go ahead and create a sub for this. So I'm gonna grab walk over here, and I'm gonna click the agent button. So we got a pop-up, and what it says, what rig do we want to use? And what's the agent's name? In our case, we'll keep it mocap biped 3. And then what's the clip name? Walk. You see there's different options here in terms of sourcing. We're using a character rig right now. You can use FBX, USD, or LOP as input. I will go into more detail on these features when I do the locomotion setup. So we can go on that. Actually, before I make this agent, I'm going to cancel. One of the things I just kind of want to stress here is that this is actually, in fact, a rig. It's not like an agent primitive or any sort. So this is a digital asset with a rig inside it. We can double click and look inside. And you can see that there are bones. There's a piece of geometry that contains the skin and deformation information. So all of that's available to you. This is a locked digital asset, hence why it appears gray. Unlocking this is fairly straightforward. You can go allow editing contents. Then you can dive in and, if you wanted to use this as a guide to making or constructing your own rigs. Yeah, so I'm going to return this to its original definition. So I'll lock it up, match current definition, and it locks back up. Okay, so let's go ahead and create an agent out of this. We'll call it walk, character rig, the path to where the rig exists, and the name of the agent we want to create. And we hit OK. So what this does is it creates a new geometry object for us called mocap biped 3 underscore setup. And in here, we have a number of things. So let's take a look at the first node. This is called an agent node. And what this is doing is it's referring to our character rig. And if we middle mouse button on this, or rather we can go over here to the info tab and bring that up, you'll see what we have is this rig is being converted into a packed agent primitive, which is represented by a single primitive or point, and we can use this. This is our agent, and this is ultimately what we're going to be simming with. So, yeah. The next thing we need to do is load some clips. So currently we have, the agent being created out of the rig, and it's using, by default, it's set up with this kind of walk clip, which is a clip that it's using to walk. And we're going to add another clip to this. So we're going to add this run cycle. So I come back up here and I click on add clip. And it says select agent to add clip to and press enter. Okay. Pick the rig, and I got some sort of error there. My apologies. We will pick the run rig. Groovy. And clip name, we will call this run. All right. Oh, made a little bit of a mistake here. Probably have my display flag in the wrong place. So this happens sometimes. When you create an agent, it sets the display flag, I believe, to the end of this chain. And if you come in before adding the clip and set your display flag to a different position, it'll do this sometimes. It'll add a new load clips node rather than just adding the clip to this current load clips node. So I'll just walk through the incorrect way to do this again. So the flag's up here. I've changed a few things. Come back up, hit add clip, pick the rig, run, and we choose the name, run, hit OK. And yeah, you can see it adds this clip off to the side here. And that's not what we want. What we want to do is add it just basically change the parameters of this guy here. So we're going to delete this guy. Come back down here to display that node, and let's try running this again. I'm leaving my mistakes in this video on purpose because if I'm running into them, chances are you're going to be running into them as well. And it's good to kind of just be able to know what some of these little gotchas are so that you can kind of bypass them. So come back up here, go add clip. It says select agent to add clip to, so hit enter, select the rig, run, and choose clip name, run. And there we go. So it hasn't added an extra node. In this case, it basically added the run to this, this load clips node. So now we have the rig, or the agent primitive created out of the rig, and it has a walk cycle and a run cycle attached to it. One of the things to note is when you do add clip, it by default changes the current clip to the last one you used. So I'm going to switch this back to walk, and we should be in good shape. Okay, so we've done that. Great. Next thing I'm going to do is I'm going to populate. So I'll just create a grid. And I will populate this grid with some agents. So let's go to populate, select agent setup, press enter. So there you go. Now select train points, train, okay. So I select the one on the right, and I'm just following the prompts along the bottom here. And hit enter, and there we go. Okay. So we have our crowdsource, which is basically our agent that we've set up with the clips. And over here we have our grid. This is getting fed into the crowdsource. There's a bunch of options on here. Again, I'm going to save the majority of this for the locomotion section. But if you want to get into the specifics of that, I kind of recommend jumping forward to that section. I just don't want to repeat the same thing twice. So anyways, we got our agents. You can control the number of agents that get seeded here. There's this agent number of agents parameter, and we got things set up for our simulation. So the next thing I'm going to do is set up a simulate. So I'm going to simulate these guys. Click on the simulate button, select crowdsource objects. So we've got this guy selected, and press enter. And then it asks you which states do you want to include in your sim. So we have a couple of clips here, right? We have the rest, run, and walk, and then the ragdoll state we didn't create, but it's kind of implied. It gives you the option because that basically gets set up within the .NET. So I'm going to click on run and walk, hit accept, and away we go. We have our crowd sim. Okay, so let's dive into the crowd sim, take a look. If you may have this turned on, ghost other objects. I've just got that turned off up here at the top of the display, just so we're not seeing things up at the object context at the same time as seeing things in our simulation. So yeah, and we can play this forward. There we go, and you can see the agent walking forward and doing its thing. All right. So, okay, let's work on doing some transitions. So I'm going to drop down a trigger, and after that I'm going to drop down a transition. We're going to basically change from a walk cycle, the walk clip, to the run clip. And to do that, we're going to change the type. We'll just do it based on time. So this is number of frames. We'll do 24 frames. And you can have a random offset. I'll leave that random offset at, say, 10, which is fine. And then we have to talk about which clips we want to change to. The input state is going to be walk, and it's going to change to the run state. Fairly straightforward. These are the defaults, so we shouldn't have to say anything. Input anything. One of the things that you'll notice here is that there's this orange bar. What this means is the simulation has been run up to frame 50, but the DOPS context has noticed that there's a change in the state. One of the parameters has been changed or something like that. So it means that the simulation is no longer valid or no longer represents the state of the parameters that we've set in this node network. So we will basically have to restart the simulation from the beginning. This is easy enough to set up. So you just hit Control and up arrow, and that will bring you back to the first frame. And if we start playing forward, you'll see that it moves forward and it changes. So, groovy. Okay, so yeah, this is a pretty basic sim. You see it's got these agents walking. There's no nothing. All this basically is a animation cycle on a particle system, and it's not really doing too much more than that. Here you can see that it's switching to a run cycle, and that you're getting some kind of skating with these agents. It's not giving us particularly desirable behavior. So we're going to look at ways to kind of adjust for this and make adjustments to velocity for an in-place animated sim. Okay, we're back once again talking about in-place animation, and we're going to talk a little bit about adjusting velocities. If we play back our animation, this is the file that we created in the last video. I've saved a copy out and I'll include it so that you guys can download this and follow along. So anyways, we could just scroll forward here in our sim. And we have our transition, but we have these agents that, are moving rather slowly, but their walk cycles are going quite fast. So you have this kind of skating thing that happens when you change velocities. So that's kind of what we're going to be addressing in this video. And we're also just going to talk about some basic structure of the DOM network and some conversations about attributes and their roles. So just to review a little bit what we have this is the simulation network that gets created when we click on the simulate button. And I'm just going to talk briefly about some of the different sections. I'll go over this again in the locomotion section, but just so you have some kind of context of what you're looking at. So this is inside of a DOP network or dynamics network. We have over here an input for static collisions. This would be used if we were using ragdolls. In this sim we aren't, but that's what it's there for. It's created by default. There's also this bullet solver, which if we were using ragdolls, the bullet solver makes use, or the ragdoll, in order to get the ragdolls to work, we need the bullet solver to get that working. So there's that. Over here we have our crowd object, which we're using to import, well, this is basically an empty container, and inside this empty container is where we're going to put our crowd information. Over here we have constraint information that we feed into that and apply to the crowd object. In this case, it doesn't really matter because we're not using ragdolls, so it's not really something we have to worry about. And then over here we have our crowd source, which is where we're getting our crowd agents from. So we can click on this link here, it brings us to the crowd source SOP. I'll just navigate back to this. There we go. Groovy. And we have over here, we have this node that says merge states. These are the states that we're going to be using in our sim. So we have run and walk. And we have transitions over here, which are controlled by this blue node. We have a trigger, which is basically when should we start transitioning from one behavior to another. So in this case, when do we change from a walk to a run? These three things get fed into a crowd solver, which is what does this actual simulation. So here you're basically accumulating the data and feeding it into a solver. And at the bottom here you have gravity. Gravity doesn't do much in this simulation because we don't have any ragdoll physics. So, and then you have your output, which is basically a node that is defining the end of the graph. Okay, so let's get back to the problem at hand. So in terms of adjusting the speed for the run, there's really fixing this is pretty straightforward. So if you look on the walk over here, we have this gate speed parameter and an allowed variance that kind of goes with it. So this is basically the speed that the agent or the particle should be going at. In this case, it's a walk cycle. For a walk cycle, the default works really well, right? But that same default doesn't work very well for a run. So if we increase this, so I'll change this to 3, and let's come back to the beginning and play forward. There you go. So that's starting to look better. Now again, this is just using in-place animation, so there's nothing like fancy like foot locking or anything like that. This is just the, you can imagine it as a particle with an agent copied to a particle. Very simple. one of the other things that you'll notice here is there's this allowed variance parameter, which is basically a kind of it's adding variance to the gate speed in terms of less than 10% or greater than 10% of this gate speed value. So let's take a look and see if we can analyze what we have going on here for speed. So I'm going to drop down a pop wrangle right underneath this merge states, and I will go. And I will name this my speed. And I'm going to use a little bit of vex here. I'm going to make an attribute, a float attribute called my speed. And I will set it to the length of our current velocity. All right, so let's take a quick look at what we've done here. And this, I basically want to be able to see my speed. So I've created this little attribute. It's not really doing anything for the sim. It's just going to give me a means of visualizing the speed. So let's examine this. Let's go to our geometry spreadsheet. I have it here. If you don't have it open on your desktop, it's very easy to open. Just click this plus tab, new pane tab, change it to inspectors, geometry spreadsheet. I'm going to navigate back to my simulation, and we should be in good shape. Great. So let's go to this geometry spreadsheet. If you've done some work in SOPs and use a geometry spreadsheet, you'll see that it's a little bit different in DOPS. I'll talk more about that in the locomotion section, but for now, let's just kind of take a look at inside the crowd object. There's a geometry section. This is basically the geometry of each of the agents. And we're going to examine some of these attributes, just kind of get a sense of what's going on. So I'm going to click on this View tab, first of all, and if you look at this list, this is the list of all of the attributes on the agents. And you can see there are a considerable number of them. So understanding attributes and how to manipulate them is going to be useful for you. So also, like, just kind of being familiar with them and being able to intuitively kind of understand what each of them are will help you. You don't need to know all of them right away. It's best to kind of think about whatever you need for a particular problem and a specific problem, and then kind of isolate those attributes and understand those and work on manipulating those. So let's isolate a few attributes. So I'm going to go hide all attributes, which basically hides the display of those attributes. And then I'm going to bring up a few relevant ones. So the first one I'm going to bring up is ID. This is basically a unique identifier for each of the agents. So when you have a crowd sim, you can basically use this identifier to do things like drive a random seed or prune or etc. The other thing I want to take a look at is we'll do the state attribute. And we will also do the clip names attribute. Great. Velocity. We're going to get the velocity attribute. That's important. We'll get the my speed attribute that I just created. And the other thing I want to get are two attributes called speed min and speed max. All right. So let's go back to the beginning of our sim here and just take a look at our geometry spreadsheet. So um, one of the things that I recommend doing when kind of creating and pruning this list is, hide all. Don't be on the first frame when you do this. Maybe do like the second frame. Mostly because what happens is when you are on the first frame, by default, the crowd sim doesn't cook until it's taken a time step. So until it's gotten to frame two. And when it goes to frame two, it'll create a bunch of attributes. So if you're on frame one and you go hide everything and then you create this list and then you step forward, it's going to add a whole bunch of extra attributes and you won't have that kind of nice, clean prune selection. All right, so let's take a look at what we got. We have the current state is walk. We have the ID. The default velocity is 1 in z, and 0 and y, and 0 and x. The current state is walk, and speed min and speed max are both set to 0. Okay, let's advance one frame. So we're on frame 2. And we notice a few things change. So the first thing that we should notice is that speed min and speed max now have values in them. And the way these are basically being set, it's the gate speed with that 10% margin on either side of it. That's what informs what these values are. So if we go back to the first frame and we set the allowed variance to 0 on the walk, and then we step forward, you'll see that speed min and speed max are both exactly the same and they correspond to gate speed. The other thing you'll notice, so let's change this back to 10, so to allow for some variance. The other thing you'll notice is when we are on frame 1, the default velocity is 1. Or the default velocity is 1 and x. And the speed, if you take the length of this velocity vector, you get the magnitude of the vector, or the length of it, is also 1. Okay, so speed min, and speed max are both 0. When I go to frame 2, the network gets evaluated and speed min and speed max get computed. Now, speed min is 1.125 and speed max is 1.375. But you'll notice that the speed of all of the agents conforms to the lower bounds of this range between speed min and speed max. Well, why does that happen? Well, it's because the initial speed is 1, right, on the first frame. So when you come up here to frame 2, and these speed min and speed max values are actually evaluated, it says, okay, like the lowest the speed can be is 1.125. So change the speed to 1.25 to kind of fit within that range. So that's what it's doing. But this isn't really giving you any sort of variation in the speed on a per agent basis. It would be nice if there was a way we could kind of accommodate this. So let's look at a way of doing this. We're going to jump out of our network and come over here to crowdsource and go to randomize. And on the randomize, there's this option for to randomize initial velocity. And you can see by default it's set to 1 and z, but you can add some randomness. So I'm going to go 0.1. Let's see what we get. All right, so we'll come back to our crowd sim, bring it back to the first frame. You can do that by going Control Up arrow, incidentally. So a nice little shortcut for that, Control Up arrow. And we go to the geometry spreadsheet and let's look at what we have. Okay, so now we have some velocities. They're set up here. And you can see that the initial velocity is no longer 1. it's now a kind of range of values. And this range of values goes between 0.9 and it looks like maybe 1 point, maybe 1 point, slightly over 1. So let's go forward and see what happens. Okay, so the speed is still getting clamped because even though we have random values, they're still too low. So let's change this. So we're going to take the gate speed and kind of use that as our initial velocity. And let's go back to the crowd source and we'll set the initial velocity to that. And now the randomness is 0.1. I think that corresponds to 10%. Let's come back to the sim and try it out. The values look a little bit more in line with what we'd expect. And let's go forward. So now we go forward and you see that these speed values lie between speed min and speed max. And we have some nice kind of randomized values occurring here within that range. And yeah, so, good stuff. And let's take a look at our sim and see what we got. Okay, so it's subtle. There's a subtle difference in terms of speed, but it's there. So, and we can, of course, verify that in the spreadsheet. This is fairly quick. They transition to running fairly quickly. I'm going to go to the crowd trigger, maybe change this to 48 frames instead of 24. So, and we should get our change over to the run cycle over here. Okay, so let's examine what's happening during the transition from walk to run over here. If we take a look at the clips, once we get to 48 frames, and there's also some randomness associated with those 48 frames, so 10 in either direction. So, which just kind of adds some nice randomness to the thing. So you'll see as it's changing from walk to run that the state stays the same until the transition is completed. But while the transition is going on, you have clip names. It will now have walk and run. The first element in clip names is the currently active state or the first state, and the second one is the state you're kind of changing to. So if we go farther enough along, and you'll see them switch over to run, and you now see this now only has run in the clip names array, and the state has kind of fully switched over to the run state, meaning that the transition is complete. So one of the other things you'll notice is as it's transitioning, the speed min and speed max are changing. They are adjusting to fit the gate speed associated with the run state. So as we go forward and we complete, let's get all the way over, you'll see that you now have new speed min and speed max, right? So 3 with a 10% variance on either side, so between 2.7 and 3.3. The problem you'll notice is that when it makes this adjustment, the speed of the agent is getting adjusted to conform to this minimum speed boundary. But once again, it's not fitting between the middle of this range. So what we'd probably like to have is a little bit of variation between this 2.7 and 3.3. But what is happening is the speed is basically just being clamped to the bottom bound of this. So what I'm going to show you in the next video is how we can use a little bit of Vex to adjust for this. Unlike what we did with the walk cycle, because the walk cycle was the initial state, we were able to alter the or randomize that initial velocity on the crowdsource operator. Um, and because we were able to do that, we were able to kind of modify that for the walk state. But now we're in the simulation, so we can't rely on that initial state to alter the run state. So we need to come up with a mechanism inside of DOPS to allow us to do that. Okay, we're back, and we're going to talk a little bit about adjusting the velocity for this run state. In our previous example, we saw, or previous video, we saw that we made some adjustments for the initial velocity in the walk state, but we notice that when we've transitioned over to the run state, that the speed is kind of clamped to minimum bounds. So we're going to look at a way using a little bit of vex and a popper angle, how to adjust this velocity and keep it within this range. So that's what we're going to be working on. I'll have saved out this file, so you'll be able to start from here and follow along if you haven't already created the HIP file from, or don't have the HIP file from the previous example. So let's start, drop down a popper angle, and we will insert it over here. And I'm going to call this adjust speed. So one of the things to note here is I'm using a popper angle, and it's underneath the run state. And the nice and useful thing about this is it will only affect the run state. This is unique to a popper angle. If you were to use a geometry wrangle and inserted this, it would basically look at the entire state of the simulation rather than just this run state. The nice thing about using this popper angle is it's whatever vex we type in here will only modify things in the run state. So that's just a kind of important little footnote. All right, so let's take a look at these attributes. We got this, and let's go ahead and make some adjustments here. So the first thing I want to do is I want to get a random speed, which is going to be kind of like a goal speed that I want these agents to kind of try and get to or surpass. So I'm going to make a float called float variable, and I will call it rand speed, and I will set it to, let's see, I'm going to make a fit. I'll type this out and then kind of explain what I'm doing. All right. So here I'm making a variable called random speed, and I am the way I'm setting its value is I'm using the ID of each agent, and I'm feeding that into a random function, and that's going to give me a random value for every agent between a value of 0 and 1, a unique value. You may be wondering why I add this kind of fractional value at the end here. One of the things, I've been using Houdini for a very long time, and one of the things I noticed about the rand function is if you have like a relatively small number of points, like 100,000, 200,000, 300,000, you can use an integer value for random, and it works well. But I found when I got into very large numbers, like millions of points, that I noticed some regularity in the randomness. And I could mitigate that or get rid of that by adding a fractional value to my ID, and that randomness would go away, or that regularity would go away. As I said, this is a habit I got into many years ago. It may actually not even be there anymore, but this is just kind of something that I do out of habit and practice, just so you know the reasoning behind it. So I get this random value between 0 and 1, and I'm going to fit that, or remap that value from 0 to 1 to be between speed min and speed max. So basically what it's going to do is give me a random value between speed min and speed max. Um, so somewhere, in the case of the run, somewhere between 2.7 and 3.3. Okay, great. The next thing I need to do is I need to get a normalized direction. And I'll explain that in a moment, but let me just write some code. All right. Ooh, little typo there. At symbol. Okay, so the issue is what I'm doing here is I'm taking the velocity. And velocity is, three components. It's a vector, and that represents two things. It represents the direction, which is kind of defined by the three separate, elements, and it also represents speed. And the way it represents speed is if you take the length of a vector attribute, that will basically give you the speed that that vector represents. So when you normalize a vector, or in this case, I'm normalizing velocity, what I'm saying is basically give me take the velocity and change its magnitude or its length or its speed to 1 and give me that direction vector, which is basically being stuffed in dir here. So the important thing to remember is that right now the velocity and dir both have the same direction, but they have different magnitudes or different lengths, or you can think of it as different speeds. So that's great. Next thing we need to do is we need to compute the speed. So I'm going to do that. The speed of the current agent. So I will do float speed, and I'm going to set it to the length of the velocity. And another typo. Okay. So for those of you who are astute, you might be saying, why recomputing the speed? You already did that down here. And the reason why I'm doing it here is I've put this here for education purposes, so that we can compare the speed with the speed min and speed max. Once I've kind of, done my diagnoses and kind of got the sim working the way I'd want to, I just turn this off and the display would go away and it would no longer be computed. But I would still need to compute speed up here. So I've kind of separated them out, and right at the moment I'm calculating speed twice, but when I'm actually running my sim, I'd bypass this and not make use of it. So I'm just using this my speed attribute for diagnostic purposes. Okay, so now what we are going to do is we're going to do a comparison between this random speed and the actual speed. I'm actually going to change the name from random speed to goal speed because it kind of makes it a little bit clearer what it's representing. Good variable names is always handy. So, all right. So if the speed is less than the goal speed, do something. So what we are going to do is if the speed is less than the goal speed, we're going to make a run go faster. So I'm going to do that. First, we have to determine how much faster we want it to go. So I'm going to go float. I'm going to make a variable called acceleration. and I'll set it to 0.1. So this is basically if this is how much I want it to accelerate every time step by 0.1 units. All right, so then let's actually reset the velocity. So I'm going to go v at v is equal to v at v plus plus the direction multiplied by the acceleration. All right, so let's just kind of go over what's going on here. We want the agent to accelerate, but we want him to accelerate in the direction it's already going. So this is what the significance of this is. We want this direction, which is the direction it's already going, with a length of 1. Now, if we have a vector with a length of 1 and we multiply it by a float, in this case 0.1, what it's going to give us is a vector with a length of 0.1, or a speed, you can think of it as of 0.1. So we're basically increasing the speed of the existing velocity by 0.1 in the direction it's already going. That's what this means. So, yeah, there's another way of writing this, which is a kind of cleaner way of writing this. And I'm including it here so that I'm going to comment out the line above it with a double slash. So these two things basically mean the same thing. The difference here is that instead of having to type explicitly say add the velocity to the direction times the acceleration, when you say plus equals, what it's saying is it's basically saying for this variable on the left-hand side of this statement, add the incoming value to things that are over here on the right-hand side, and then assign it to the velocity. If you're not too familiar with Vex, this might be a little bit confusing, but I wanted to include it here just so that you're aware of the syntax and what it means. If you're using somebody else's setup, they may have something like this. So I think that's kind of important to know and see. All right, so let's go back to the beginning of the sim and play it forward, recompute, and see what we get. All right, so here we have our speed min and our speed max between 2.7 and 3.3, and then my speed is now kind of randomized between the threshold. And instead of having all the values with a speed of 2.7, we now kind of have a nice random mixture of those speeds. We can play forward our sim. And, it can be subtle, but it adds a little bit, some variation to your sim, which kind of will make it, richer and look less mechanical. So that's this is basically how you'd use Vex to kind of alter the speed of these agents. Now, one thing I should mention is that adjusting if you're using in-place animation, you can adjust the velocity directly. So you can do something like what we're doing here, where we're just adding a new value to the velocity and adjusting it. This is one of the things that you can do with in-place animation, because it's basically just particles and agents copied to particles. So it works very much like a particle system. If we're using locomotion, which we're going to get to next, you cannot use this mechanism. There's a different mechanism for adjusting velocity of a state. And being aware of that difference is important, and appreciating that difference is important. So keep that in the back of your mind, and as we work through the locomotion examples, you'll you'll I think in the trigger section, one of the examples in the triggers shows how you can manipulate velocity for locomotion agents. So anyways, with that, I'll see you in the next video, which will be locomotion. And yeah, see you then.